Okay, so the title of today's talk is MEMS Aerospace Applications and Environments. I'm Gary O'Brien, an NG Fellow from Launch Vehicles at Northrop Grumman. And what we're going to talk about is two applications, sensor applications for space exploration that launched in 2021. The first is going to be this MEMS micro shutter array for the near-spec instrument on the James Webb Space Telescope. And the second will be on that Mars Ingenuity helicopter that was attached to the Perseverance rover as shown here. So let's see if we index. There we go. So with this MEMS micro shutter array, we're going to go into more detail. Before we do that, I just wanted to note this is a joint venture, the James Webb Space Telescope, between the Canadian Space Agency, European Space Agency, and NASA. And the ellipsis is supposed to show there's just a ton of subcontractors, of which Northrop Grumman is the primary system integrator. And you can see here, after the telescope's been folded up onto its launch pedestal, it got sent to French Guiana, and it was launched on an Ariane 5 rocket on December 25th, 2021. Now, if you look at the 18 panels for the primary mirror, they're made out of beryllium. When you polish beryllium, it actually reflects mostly in the visible spectrum. So it looked like a bathroom mirror, for a good example. So what they've done is they've evaporated 100 nanometers of gold to make it a long wavelength infrared reflective material. So that's important. Now, the beryllium was chosen because it's very stiff and strong and lightweight. That means it's easy to put into orbit from a cost standpoint. It also has a very low coefficient of thermal expansion, which is important for cryogenic temperatures near minus 233 degrees C. And it's got low amplitude mirror vibrations compared to titanium and aluminum. If we look at these three cantilever beams that are made from titanium, aluminum, and beryllium, note that the beryllium has much smaller amplitude vibrations at higher frequency. They pull images from the James Webb Space Telescope. At the bottom right, we see Hubble. At the bottom left, we see James Webb. So Hubble had a polished aluminum alloy mirror. Hubble has that beryllium and gold. There's a person down there to show you the scale for that particular instrument. Now, let's look at the Hubble Space Telescope first. If we look at that, it was really set up mostly in the visible spectrum with a little bit of near-infrared, where the James Webb Space Telescope is going to be in this long wavelength infrared region. Now, why is that important? Let's look at this image at left, this one here that Hubble took. Now, these are both Hubble images. One's in the visible spectrum, the other one's in the near-infrared. And if we look in a little bit more detail in this area that's circled, notice that gas and dust are blocking visible wavelengths, and we really can't see these stars back in this region, but here it's very clear. And this is just near infrared. Remember, James Webb is going to be far infrared, so we're going to see much further in distance, and further in distance is further back in time because it's space-time. So this is going to be important for Hubble to look further back in space with that long-wave infrared capability. In addition, the primary mirror is going to go from 2.4 meters on Hubble to 6.5 meters of diameter. With this hexagon packing, that's over a 5x mirror increase in area, which means just a ton of resolution enhancement. So now, why is this important? Well, if we look at the James Webb, it's going to see back to about 300 million years after the Big Bang. And right now, this is kind of, for lack of a better term, it's a dark area for astronomers. They have theories about what happens here, but they really don't know what's happened before a billion years after the Big Bang. Now, the furthest the Hubble Space Telescope is seen on a single star, it broke its own record on March 30th of 2022, just recently. It used gravitational lensing to look at a single star, and this is the furthest one we've ever seen. This Hubble Deep Field is looking at galaxies, and these are long exposures, but the farthest star it's seen is about 900 million years. That means the James Webb will be able to see about 3x further back in time than the Hubble Space Telescope. So this is going to be huge for astronomers to fill in their gaps for their theories about how early first galaxies and first stars form. So how does light get into the James Webb? Well, essentially you've got a light column that's going to come in and hit that primary gold and beryllium mirror. Then you'll get a first bounce. And then it'll hit the secondary mirror. Another bounce. Go through a lens and invert. And then we'll get a few more bounces. And what that's going to do is it's going to go to these pickoff mirrors. Now those pickoff mirrors are connected to 4 primary instruments, of which the near-spec, the near-infrared spectrometer is 1. So 1 of 4. And this is where the pickoff mirror is. So some of that light will be diverted through this column. This is where the micro shutter array is actually installed. And this is a picture of 1 of 4 of these micro shutter arrays. So if we look in a little bit more detail, you'll see this is made up of pixels in its row column address. So it's 384 by 175 in one of these little arrays. And with 4 together, it's about 269,000 shutters. They're 200 microns on the long side, 100 microns on the short side. The trench is 2 microns wide, and the torsion spring is 2 microns wide. A lot of 2s in there. So it's easy to keep track of. So essentially what you've got is, again, this is put in the optical path to give it high contrast for the images that it wants to look at. So if you want to actually index these, They use a row column technique. So if you look at a video, you can actually turn pixels on individually for the piece of space that you want to look at. And this is an indication of how you can turn those pixels on individually. So what's going to happen is James Webb's going to look at the sky. It's going to have a shutter mask in between that and have an optical sensor. In this case, it would turn on the shutter mask with 3 examples and then do a selection spectrum. Now, this selection spectrum lets you look at the chemistry of the space that you want to interrogate. And by only picking a few pieces of space, you get a higher contrast, so you get less noise from the areas around it. And this really is trying to look at the chemistry of space, because we're looking for the chemistry of life with that near-spec instrument out in space. So now, how does this work? Well, essentially, again, from the pickoff mirrors, some of that light's going to be diverted. It's going to go into the near-spec instrument and get its first bounce. Consequently, just to let you know, this is silicon carbide, this whole pedestal. Now, these mirrors, you're going to see a few bounces, and you'll see this filter wheel spin. This is important, because this is how the spectrum analysis is done. It's going to look at one image and then do a long analysis, change a filter wheel, do a long analysis, change a filter wheel. Now, this is the micro shutter array here, and that's a picture of it in this location. So this is when it goes through the micro shutter array and actually picks out the high contrast area. Now, on the other side of the micro shutter array, this is where the light would actually bounce through the instrument. So we get a few more bounces. Now it hits a grading wheel. And now it's going to come up to the optical sensors in the instrument. And there's 2 optical sensors that are up here on the top. Now, you're going to pick the shutters that you want to interrogate the sky for. So in this case, it would just be this one selection. And then that color filter wheel is going to spin, and we're going to get multiple spectrums on that piece of sky to actually look and see what the chemistry is. Now, after it's gone through its multiple color wheel, what you end up with is Fraunhofer lines. And there's the color wheel that's put in the optical path. Now, these Fraunhofer lines are important. They actually tell you what the chemistry of that particular piece of space that you were looking at is. And this is why far infrared is important. There's really strong signatures for Fraunhofer lines for water, methanol, carbon dioxide, methane, and ammonia. This is the chemistry of life. And this is really where the James Webb Space Telescope is going to focus most of its attention, trying to look for life out in deep space. So now let's look at this image. We already talked about a lot of this information. I just put this figure up here so you can see how large the array is with respect to a human hand. And then this is the process flow. So if you look as far as the shutter array, with a 3x3 array, it's got row and column. So this shows for a 3x3 array how you could turn on 1 pixel. Okay, this is the process flow. The pixels themselves are made from aluminum molynitride and infrared. But notice these gaps were 2 microns. So what's done is this substrate is really a light shield. It gets bonded on with indium bumps. And what that is, it's for light leakage. So the light would actually come through this direction, and this blocks that 2 micron gap from letting light leak through to give it higher contrast ratio for that particular instrument. So now some of the early work with the MEM structures, this would be where the light would go in this direction and the light would come out of this direction. So this would be the bottom and the top. These were really smooth sidewalls, and they had some issues with stiction. In fact, they had a ton of issues with stiction, as you saw from the earlier figures. And what they did was they put stiction bumps on the inside for an open shutter, and for a closed shutter, they put in small anti-stiction bumps that were 1 microns wide and about 2.25 microns deep. Now, there's a ton of work for the actual arrays that are on the James Webb. Most of that work was published in SPIE. You can find it prior to 2008. But there's been just a ton of work in recent years in both Japan and the United States. What they do is get rid of this magnet because it's very complicated and it adds a lot of complexity to the system. They used a plus or minus 20 volt array scheme for the row column addressing. These new researchers are trying to go above 100 volts and get rid of the magnet. But let's go ahead and focus on what's on James Webb that uses a magnet and explain how that works. So you'd have a set of closed arrays, and then you'd sweep a magnet underneath it, end up with a partial actuation, so partially open and closed. And then for that last 5%, you're going to use an electrostatic force. So shown here, this would be about 95% using the magnet to pull it down. And that molybdenum nitride is magnetic. That's what actually gets pulled down with the shutter that's striped on the top of that shutter array. And then that last 5% is electrostatically pulled in and held. Now, I put this figure in. This shows the magnet in a linear array. So there's a permanent magnet out here, and it actually gets pulled across the array with a linear actuator, as shown here. So now let's talk a bit about testing and qualification. It was tested at 200 K rads of total ionizing dose. This is much higher than you would see at an L2 environment. That's fine. It's always good to overtest. It was tested at 35 K for 100 K cycles with greater than 90% yield as their criteria. And their vibration, they use a shaker vibration profile that's provided by the Ariane 5 launch vehicle team. Every rocket has a different vibration pattern, and you have to get that from your vendor. So if you switch rockets, you're going to have to requalify your vibration profile. Just keep that in mind. So it's usually not a good idea to switch late in the game. So the James Webb Space Telescope is at L2. L2 is shown here. There's 5 Lagrange spots for an Earth, Moon, Sun system. These are all zero gravity spots. This is chosen because the middle of L2 is a zero G spot, so it takes a minimum amount of fuel to maintain this orbit at this location. Now, 150 million kilometers is 1 astronomical unit. This is only 0.1 astronomical units away from Earth. That means it's only 1% further away from the sun than the Earth is from the sun. Now, correspondingly, that means if we look at things like radiation power and radiation pressure, they're only about 1% lower. So this is essentially almost like having it in low Earth orbit. Now, as far as temperature, the hot side's 85 degrees C, the cold side's minus 233 degrees C, and it always sets up in this orientation where this side always faces the sun, and this side is always faces the dark. In fact, if it ever rotated accidentally, there would probably be significant damage to the telescope because of coefficient of thermal expansion, so that would be a problem. And then there's a picture here at our Northrop Grumman facility that shows the solar shield with people, just to give you a scale on how big that solar shield is. Now, what we worried about is radiation, and we don't care about non-ionizing radiation. We care about ionizing radiation. It's bad for people, it causes cancer, and it kills electronics. We have 3 sources of radiation for spaceflight: trapped ions. These are protons and electrons in the valence belts, protons here, electrons here, and solar energetic particles from coronal mass ejections and galactic cosmic rays. Oh, one other thing. Let me go back and talk about this real quick. The other thing is, if we look at shuttle, remember, the space shuttle serviced Hubble 5 times. It changed the gyroscopes out 3 times, all 6. The gyroscope is the weak link on the Hubble Space Telescope, and when it dies, it'll because the last 2 gyroscopes died. So keep that in mind, MEMS gyroscope people. Yeah, and there's no way to service the James Webb at L2. The furthest humans have ever been was Apollo 13, about 400,000 kilometers. So it's really on its own. So the next thing we want to look at is, and this is a little complicated, but I'll go through it quickly, total ionizing dose. This is in K-rads out here. Okay, this is a 100% lethal dose for a human at 1 K-rad. And if we look at 0 degrees for this, you can see the peak for the inner belt and the outer belt is at 0 degrees. This is 0 degrees latitude. This is the equator. So let's get our bearings. If you look at the moon missions for Apollo, they flew the astronauts at about 35 degrees to the Van Allen belts. This was their kind of most dangerous point that was known during the mission because this is the highest radiation. So they skipped the inner belt, went through the outer belt, but they went through it very quickly. So it's very important to stay away from those outer belts. It's where the radiation is really high, and you can see that's where those peaks are. So another thing to think about is we try to keep satellites at LEO, low Earth orbit, and geosynchronous orbit, because the radiation is pretty low, and you can actually get away with using some COTS parts or commercially available off-the-shelf parts in these areas, especially for Hubble and the International Space Station. If you look at pictures of astronauts, you'll see them, unfortunately, with their Apple phones and iPads and other electronics. So no plug for Apple here. Okay, so yeah, that's probably enough about that slide. Before we go off, notice that there's a glut of satellites here. These are GPS satellites. These are strategic rad-hard. They have to survive a megarad of radiation. They're in that particular orbit. They have to go overhead every 12 hours. So they have to be in this site. So these are literally right around a megarad of radiation. So they really are designed for a radiation environment, much beyond what you'd see for something at L2. As you can see from the graphs here, the radiation environment at L2 is much lower. Really, we only have to worry about galactic cosmic rays. We get a pretty good shielding for solar protons when we use aluminum to shield. But galactic cosmic rays aren't shielded well at all by aluminum. The other thing I just wanted to note is the lethal dose for a human, again, was 1 K-rad, which we talked about before. If you look at most COTS triple E parts, and this is electrical, electronic, and electromechanical, what you'd find is you get about a 1% VT shift right at about 1 K-rads. So if a person gets his lethal dose, that's when you start to be able to see a shift in COTS electronics. They typically fall out and die somewhere between 10 and 100 K-rads. Okay, and if you want something to function at 1 megarad, you have to design for it. That means design for rad-hard and process for rad-hard. It's actually both. Okay, so another telescope that was out at L2 was Herschel. It was there from 2010 to 2013. And you really can't deal with shielding with galactic cosmic rays. Lead doesn't work for this type of radiation. It works great at your dentist for X-rays, but it doesn't work for gamma rays well. In fact, it'll probably make the total ionizing dose worse. So what we like to use is things like water, plastic, phenolic, anything that has hydrogen in it is a great radiation shield. Don't use lead. I don't. And then the next student that tells me, why can't we use lead? I'm going to have a nervous breakdown. Okay. The only thing I wanted to talk about here is, too, when you look at galactic cosmic radiation, these are soft errors. When these hit, they hit with such kinetic energy, they have enough energy to knock the to 0 or a 0 to a 1. But it doesn't damage the electronics with a total ionizing dose. It's just change your bit state. So if you recycle the power, that part's fine. In fact, what you do is if you use error correcting code scheme for your memory, you're really fine. And what they found in this 3-year period is they had about 1 bit flip per day for this Hubble telescope at L2. So it's really doable as long as you use good system design. Okay, so what's next? Well, you know, this is James Webb, Hubble, and this is what they want to do. It's not Louvois, it's not French, it's Louvois. It's large UV optical IR telescope. It's like a super Hubble, and it's going to use that same origami approach that James Webb used. So big telescopes need big rockets, so you're going to need something like SLS. And this was rolled out on March 17th this year, so it's actually at the pad. So let's go ahead and talk about the helicopter a little bit. First, let's talk about the weight. Perseverance weight's about 1,000 kilograms, and then we're close to 2 with the Mars helicopter. It's about a 500x difference here. Now let's talk about the power supply. This one uses plutonium dioxide, and it's a radioisotope thermoelectric generator, an RTG. It costs $75 million. It gives you 14 years of continuous operation, which is important because you wouldn't want to use a solar panel for this type of an operation where dust can give you a problem on Mars for power. And that means its safety factor is 4x because it only is slated to last for 3 years. So and this is really a serious science instrument. The batteries on the Mars helicopter cost $5.99 a piece. These 94 cents plus tax and shipping, and you can buy this online. So if I can, yeah, there you go. So you could buy this online. You could actually fund. In fact, it's the same battery type that's used in a Tesla or just about all the electric vehicles that are out there. So it's kind of a nice takeaway. The other thing to think about was the pressure on Mars is only 1% of Earth's pressure because it has no magnetic field. Air is stripped away from the planet constantly, or gas is stripped away. So they wanted to put this helicopter in just to see if powered flight was possible. But as of the 23rd flight, now it's a scout for Perseverance. So this thing is amazing. Now, what I wanted to talk about was look at this power cycle. And then you could see some dust on top, and they had to do a couple of maneuvers to knock dust off the solar cell. But every night, it gets down to about 90 C where this is located. That's too cold for a lithium-ion battery to survive. So it has to use 21 watt-hours of its 36 watt-hours of daily recharge cycle to keep these batteries warm enough to survive. Even the mission planners are surprised this thing is still alive. It's amazing. And its 25th flight, which just happened last week, was its record, 161.3 seconds, 704 meters, 5.5 meters per second peak speed. It would have taken Perseverance 5.87 hours to make that same distance. And the reason that this is not a blistering speed is they lost the Spirit rover that got it stuck in sand in 2009. Remember, when Mars is close, it's a 5-minute radio communication between Earth and Mars. When it's far, it's 22 minutes. So the poor ground controllers have a lot of issues trying to keep up on the rover, so they keep them slow. Okay, this is the fun part. If anybody's here from this JPL team, I owe you a beer because I love this design. They used ARM MCUs for the primary flight computer. They used a Snapdragon processor and a Xilinx rad-tolerant, not rad-hard, rad-tolerant FPGA. Everything you see here, you could buy off the internet. You could fund this whole program yourself, which is amazing. And it's just been an amazing demonstrator for helicopters on Mars so far. Let's look at the IMU. It's a BST BMI 160. And look at this. It pulls 925 microamps in its full power mode with the 3-axis accel and the 3-axis gyro, and it's only 1 gram compared to 1.8 kilograms of total weight for the helicopter. So when I look at this system, I love the fact that they used a secondary or a spare flight computer. I would have put 2 IMUs on for sure and 2 nav computers, but I usually design for human systems. In fact, when I design a system that's non-human rated, I do 2 IMUs, and it's human rated, I usually use 3. So if you look at any of the NASA systems, you won't find anything with less than 3 IMUs if it's a human rated system. Okay, so let's look at radiation. NASA's had a problem in the past with radiation in their astronauts. This is dosimeter data over the years. Up here, this is where we think deep space transport is going to go, and this is Mars mission profile. So what you can see is the Mars mission profile is pretty high. In fact, the next tick up is a lethal dose of radiation. So really, what you'd want to do is send robots like this, especially these low-cost secondary robotic probes, to kind of look out in areas for good human habitation spots that aren't going to be a problem for radiation. And when I talk about radiation, let's look at Apollo. If you look at Apollo 14, they had a high mission, Apollo 14, that had a 1.14 rad dose for the astronauts, and this is because of solar weather. There was a coronal mass ejection. It did not point at the Earth-Moon, but we got a side lobe. And because we got some radiation, it means that they got a higher dose than was expected. Now, keep in mind, Apollo 16 launched in April of 1972. This launched in December of 1972. There was a coronal mass ejection from the sun that received a fatal dose of radiation. There's no way to protect them with the lunar landing module, and there was no shielding that would have protected them from that. And we still have this issue today, so this is something that needs to be solved in the future before we go to the moon and Mars. So, and remember, the Carrington event was in 9/1/1859. This is the largest recorded solar event of recorded history. But we had a similar event that was a near size to that during July of 2012. It missed us by 8 days. The sun rotates with respect to us every 25 days, and that CME pointed out into space away from the Earth and the moon. If that would have hit us, we'd have a lot fewer satellites in orbit right now, and we'd really have to worry about the astronauts in the International Space Station. So don't think because it hasn't happened yet, it won't happen. And I have to design for radiation, so this is always the first thing I think about. Now, when I look at these deep space probes and I see the Mars helicopter, God, I'd love to find one of these skylights and see what's inside, see how big it is, see how large the tube is inside, because this provides instant radiation and micrometeorite shielding for your astronauts. And these lava tubes are rills. Most of the time, there's a walk-in at the end of the lava tube. The skylight is part of the lava tube where the ceiling has fallen out, and we see these all over Mars. So this is an example of a skylight on Earth. The largest ones are 15 meters across. The ones on Mars are about 50 meters across. The lower the gravity, the larger the skylight. So the gravity on Mars is about 1/3 that of Earth. Okay, so you're going to find very large lava tubes that would be big enough to put a settlement or an inflatable. Oops, let me go back to that. An inflatable structure like this inside one of these structures and actually protect astronauts from micrometeorites and radiation. Now, if the skylights on Mars are 50 meters, the ones on the moon are 100 meters. And when we look at that, that's because the gravity here is 1/6 that of the Earth. So some of these are really interesting when it comes to the skylights that are on the moon. So at 100 meters across, the width of this particular lava tube can be kilometers wide, and they're tens of kilometers long. So what a great spot to go explore to try to put some kind of an outpost. Now, this particular mission from JPL, that's not what they're doing. They're geologists. They actually want to go down and look at the layers as it goes down into the skylight, because for them, that's how they walk back in time as they go down layer to layer. But I think if you coupled like a lander with a tether that goes into the skylight, this would be a great way for us to actually search for better places for our astronauts as well. And remember, if it blocks radiation and micrometeorites, it blocks RF. You have to have a way to communicate, and that's why that tether is important. Now, this is the other thing to think about. If you look at a Hohmann transfer, this is the lowest fuel that you require to actually transfer from Earth to Mars. Remember, when it's near, it's 56 million kilometers away. When it's far, it's 401 million kilometers away. That means it's 5 to 22 minutes, depending on whether it's near or far for radio communication. The moon's pretty much always the same distance, 360,000 kilometers and 406,000 kilometers. So, and it's 1.3 seconds of radio communication. We have a logistical kind of identical. Murdo Station would be a great example of how it would be for us to get to the moon. It only takes 3 days each way. So we really should think seriously before trying to conquer Mars before we actually have the moon set up as a standard outpost for human exploration. And that's kind of where I'm going with this. I see sensors and little robots like this actually moving forward, trying to find something like this, which is probably what I consider to be a walk-in for one of these lava tubes, where you could put inflatable structures and drop mesh networks so we can actually communicate with the probes as they go inside. So again, moon first, Mars second. Let's keep it safe for people and use robots. So big rockets are what's going to take us to the moon. This is one that showed here. This is an SLS. 35 of these have been actually fired off from 1987 to 2020. These first ones that are in green were verifications for the redesigned solid rocket motor after the Challenger disaster. This is me in 1987. I look the same, right? Just checking. And essentially, this is the last one. So I was actually the design engineer for this one, for the sensor package. So I was out in Utah for this one. And this is at our Northrop Grumman facility out in Utah. So if you actually look at one of these tests, this is what it looks like. Let's see if I can get the video to roll. Oops, couldn't get the video to roll. Try it again. Boom, no video. Sorry, there was going to be a video right there with a rocket burning, but I guess we're not going to see it in this particular presentation. But what you've got is all the rocket plume comes out in this direction, and we have a 4 million pound load cell that's connected to a concrete structure that goes 160 feet in the ground. So we measure the actual force on the transducer to see how much thrust you get, and then we correlate that to pressure. So this is the thrust profile, and this is actually measured. It's not calculated. So for real, there's really a 4 million pound transducer on that pole. So it's amazing. And what you get is this is what one of these solid rocket motor segments looks like. So this is for a space shuttle. It uses 4. SLS uses 5. These are the same solid rocket motors that were used on the space shuttle. In fact, all the solid rocket motors for the first 7 launches of SLS have already flown in space on the space shuttle. So they're just being reused. So what's done is this star pattern in the front is it's our special sauce. These segments that are back here are usually just conical cross sections. But this one gives you a thrust profile. And what's done here is we put a thrust notch in. We actually throttled the solid rocket booster down through max Q, so we get a lower load on the rocket itself. So it's kind of cool. And if you actually correlate thrust to pressure, this gives you a way to just measure pressure on the forward dome. This is the forward dome here during launch, and actually know what your thrust is for your vehicle. In fact, this is what's done for the solid rocket booster. It goes down to 75% of its peak thrust right at that max Q point. And this is what the maximum dynamic pressure on the vehicle is, so it doesn't damage any of the leading surfaces or the windshield for the orbiter. But actually, in the case for the SLS, it'll be that nose cone for the core stage tank. So, and this also shows where the RS-25 liquid motors actually throttle down as well. So the liquid motors are throttling down, but so do the solid rocket boosters. And a lot of people don't know how complex and complicated solid rocket boosters are. The pressure sensors that are on the forward dome actually are what separate the vehicle. When they get down to below 50 psi on both boosters, that's what initiates separation. So I got it. So if we want to look at the pressure sensors that are on the forward dome, these 3 in the blue were the ones that were used for the space shuttle. There's a 4th one for SLS, so now we have 4. 4 is always better than 3, right? That's a joke. 3 would have been fine for the structure. These are really durable pressure sensors, but they're old. This is the same pressure sensor I used to install when I worked on space shuttle. It hasn't changed. And essentially what you get is it's an analog output. And I hate that because that means I have to run this back to an ADD converter in an avionics box with a twisted pair coaxial cable. That also means it's heavy. This requires a ton of weight. But the reason that we use this, and it's kind of funny because I did an audit at this factory 2 years ago, and they had SpaceX pictures up everywhere. So they were really thrilled to tell me SpaceX was their biggest customer. So it's not just us using this company, everybody is, and there's one reason, this. So if you look at this block, which I made bigger here, they actually list their total ionizing dose, how much their part can take, and believe me, there's almost nothing in here. This is a 1980s macro pressure sensor that is really ridiculously simple. So wouldn't it be great to take off-the-shelf automotive MEMS brake pressure sensor that already gives me the spec I need, but I don't have that radiation TID? I need to know from you guys, what's your total ionizing dose capability? What's your sensitivity? And you might be pleasantly surprised. If you have a lot of metals in your CMOS flow, you might be pleasantly surprised that you have some pretty good shielding. You're probably in that 10 to 100 K range. If you've got a cheap process flow, you're probably in that 1 to 10 K rad range for total ionizing dose. But if you knew, and I knew you had a part that had a pretty decent radiation tolerance, I'll characterize it. But this is a chicken and egg problem because there's so many parts out in the field. Which ones do I do? Because I have to do all the radiation testing, and I hate doing it, and it's expensive. So my challenge to the community is, when are you guys going to start doing this so we can use MEMS parts? Because this is a digital output. I can be on a bus, and I can use one set of cables for all my sensor arrays. You have no idea how much weight that saves. And with that, I'm done. So thank you for your time. Please.
Great talk here.
Yeah.
Really enjoyed it. So, were there any MEMS seismometers on any of the space flights for the James Webb?
For James Webb, no.
They didn't care about having a seismometer?
Well, they have sensors on there for vibration,
Right.
but it's not like a seismometer for ground. But what was the first seismometer on Mars?
I don't know. That's why I'm asking.
Actually, the old ADI guys will probably know. There was a Mars mission that actually had one in the 90s. So the first MEMS device that actually went to Mars was an old ADI and a TO can. It was what is it, XL50?
But is that good enough for the seismometer?
No, it was just a first mission. Right. I digress. It's actually on slide 74 as a backup slide if you want to see it.
So no MEMS inertial sensors went on the James Webb?
No, and actually, if you look at the IMUs that are used for spaceflight, there's no MEMS anywhere. They're typical HRGs now. So the resolution has to be so high because you're going to use that IMU in addition to your star tracker data. If you've got an optical star tracker that tells you where you are in space, you look at 3 different stars minimum. Then you figure out where you are in space, and then you correlate the IMU to that spot. And that's how you reset your error from the IMU from that point. And then every time it does a star tracker, it resets the IMU error. So anybody else? So this was perfectly clear? No problem? So I'm sure most of you would never take my class now. Go ahead. Ah. Hi, Christian.
So it was very inspiring. So my question is, what can we learn here on Earth? Bring your presentation back from the space to Earth. What can we learn specifically for the safety and security of space?
Well, that's a good question. Most of the aerospace sensors we use they're pretty old and tired. They need a facelift, for lack of a better term. They need to be re-energized. We're slowly having to build sensors ourselves internally that can go on to faster even Ethernet networks so we can use the data more real time. And we're actually kind of tracking what's going on in the automated vehicle space. So I spent a couple of years in the automated vehicle space with you as well. So we're actually kind of tracking behind that, and real-time operating systems are becoming more and more important as well for the same reason, because you want to be able to correlate multiple sensors over the vehicle and put that data together. So it's really the same problem, but our technologies, because they've been qualified for so long, it's hard to get people out of the mindset of, hey, it's not broken, don't fix it. So, it's difficult. But if you could give me that total ionizing dose on your spec sheet, like I said, radiation testing is difficult because it has a lot to do with whether you test the part while it's on or it's off, and is it total ionizing dose or is it a soft air? So there's a lot of different flavors there. But if I just know your TID, your total ionizing dose, is pretty high, like if it's in that 10 to 100K range, I'll probably grab your part and beat the heck out of it and just see what it's got and try to fit it in some spots. Because for rockets like Space Shuttle, this one only goes to 47 kilometers before it's separated from the vehicle, okay? That means my radiation environment's about 200,000 kilometers. For some reason, NASA makes me use 200,000 instead of 47. They're going to let me back it down to 47 after the 3rd launch of Artemis. That's what I've been doing for the last 3 years, and that's why I'm so freaked out about radiation. But when that happens, we're going to be able to use these EEE parts. And that's a program from NASA. If you look it up on the web, EEE parts, electrical, electronic, and electromechanical, they want us to use MEMS parts, okay? But they're just being very slow about it. But they realize that's where the cost savings is going to come in from weight and power consumption and volume. So, and that's kind of where the future is going.
I think we're going to have to get Jason's question with the break.
We can do that.
That's Gary's time, but...
Yeah, thanks.